All right, let's just dive right into this explainer. Today, we're doing a full technical system design review of something that frankly shouldn't even be possible. We're talking about DeepSeek V4. Now, as we evaluate this massive 1.6 trillion parameter AI model, we aren't just going to look at what it does on the surface. Instead, let's put on our lead architect hats for a bit. We're going to dissect exactly how the team built this under some truly extreme constraints, basically relying on pure mathematical innovation to completely rethink how massive AI architectures are designed, trained, and deployed.
So here is our system blueprint for today. We'll quickly cover their engineering constraints, then move on to solving the attention bottleneck, taming trillion parameter signals, choreographing GPU hardware pipelines, stabilizing AI training dynamics, and we'll wrap up with what this means for the future of efficient AI. Let's get to it.
Okay, part 1, engineering constraints. Building at a 1.6 trillion parameter scale. When you look at this project, the sheer audacity of their goals compared to their actual infrastructure is just glaring. Imagine being handed these constraints. You've got an engineering team roughly 40 times smaller than OpenAI's. You have severely constrained compute capacity, and you have literally zero access to the top-tier industry NVIDIA chips. Despite all that, the target is a 1.6 trillion parameter model with a 1 million token context window. Just to put that into perspective, a million tokens is about 750,000 words. That is like feeding the AI the entire Harry Potter series and expecting it to perfectly recall one specific sentence from book 3. You absolutely cannot just brute force a solution here. You have to get creative. Which brings us to part 2, solving the attention bottleneck by completely reimagining memory. See, at a million tokens, storing intermediate results in the key value cache becomes an astronomical bottleneck. It just completely chokes the GPUs. So DeepSeek solved this using a really clever hybrid attention architecture. First, you have compressed sparse attention, or CSA. This takes small chunks of 4 tokens and merges them into a dense summary. Then you have heavily compressed attention, or HCA, which acts kind of like a macro lens, aggressively grouping up to 128 tokens into a single representation. Inside the system, their lightning indexer selectively retrieves what it needs. Think of it exactly like a student skimming textbook summaries and only jumping back to read the highlighted chunks when they're actually relevant. Now, you might be wondering, if you compress everything, don't you lose all the precise details? Well, yes, and that's exactly where sliding window attention comes in. While the other pathways are aggressively compressing the distant past, this parallel mathematical pathway continuously tracks the most recent context with perfect, uncompressed exactness. It preserves that high-fidelity, immediate context, giving the model a really sharp, localized focus without absolutely crushing the memory. And the result? By interleaving these 3 pathways, the team managed to reduce the KV cache memory footprint by a staggering 90%. So for you, as an engineer or a user, this means massive context windows are no longer completely bottlenecked by hardware memory. It's a real game changer. Moving to section 3, taming trillion parameter signals, or as I like to think of it, the math of stability. At this massive scale, when you start stacking dozens of layers, you get something called a signal explosion. You know how placing a microphone too close to a speaker creates that deafening, screeching feedback loop? The exact same thing happens here, and it'll crash your entire training run. Since standard residual bypass lanes fail entirely at this scale, the team introduced manifold constrained hyperconnections, or MHC. This is a hard mathematical rule that replaces those standard bypass lanes entirely to physically prevent signal amplification. This quote brilliantly illustrates just how elegant their math is. They literally force the residuals to behave like a doubly stochastic matrix. By using something called the Sinkhorn-Knopp algorithm, they run about 20 iterations of normalizations right before each layer processes the signal. Because every single row and every single column must mathematically sum to exactly 1, the total signal is physically forbidden from blowing up. They essentially mandated a law of physics for the math to prevent that feedback loop. Okay, section 4, choreographing GPU hardware pipelines. This is all about squeezing every ounce of performance out of the silicon. So enforcing a 20-step stabilization loop before every single layer, that introduces some severe, potentially fatal compute costs. Plus, with a model scattered across hundreds of server racks, waiting for data to travel means you are bleeding money and time. To solve this, the engineering team choreographed these incredible data transfer waves. While the GPUs immediately process Wave 1 data, Wave 2 data is actively traveling over the network cables in the background. The computation and the communication overlap perfectly. This completely eliminates idle GPU time across the clusters. No one is sitting around waiting. To handle the massive compute overhead of that 20-step loop, the team used deeply optimized custom fused GPU kernels written in Tlang. This hyper-optimization shrank the computational overhead of those strict mathematical constraints down to a mere 6.7% of runtime. Just incredible efficiency. But writing custom fused kernels by hand is notoriously error-prone, right? And at 1 trillion parameters, even a microscopic error will silently corrupt the entire model. So they couldn't just test the low-level code and cross their fingers. Instead, they actually used a theorem prover, the Z3 SMT solver, to mathematically guarantee that their code was absolutely, provably flawless. No guessing allowed. Section 5. Stabilizing AI Training Dynamics. Let's look at how they actually go about teaching this massive model. You don't just dump 33 trillion tokens of data into this engine all at once. They used a really smart curriculum training method. Phase 1 starts with just 4,000 tokens so the model can learn basic grammar and syntax. Then, Phase 2 stretches it out to 16,000 tokens. Phase 3 moves to 64,000, and finally, Phase 4 opens up to the full 1 million token working memory. It's essentially like slowly expanding the working memory of a brain while it's still figuring out how to think, preventing it from just drowning in data. During this training process, they completely replaced the industry-standard AtomW optimizer with their own custom muon optimizer. Muon works a lot like tuning a guitar. It uses a two-phase mathematical shaping approach. Phase 1 makes these really fast, aggressive adjustments to push the model toward convergence. Then, Phase 2 switches to tiny, precise micro-tweaks for perfect pitch stabilization. It vastly outcompetes the standard method of just making direct adjustments across the board. Even with all this, at this ridiculous scale, training runs can still experience loss spikes where the math just suddenly blows up. Now, the standard industry fix is to stop the entire run, roll back to an earlier save, and try again. And as you can imagine, that is wildly expensive. So, DeepSeek introduced anticipatory routing. Think of it like reading a stock chart. It monitors internal statistics, and if it detects a spike, it relies on historical moving averages to ignore the chaotic daily noise and lock on to the true underlying learning trend. The system just self-stabilizes in real time. And finally, Section 6, the future of efficient AI. It's all about elegant math over brute force. Let's step back and look at the ultimate results of this flawless infrastructure blueprint. Despite their massive resource constraints, DeepSeek V4 runs on just 27% of the compute of their previous V3.2 model. It matches or outright beats top-tier closed models like Opus 4.6 and Gemini 3.1 Pro. It achieved a literally perfect 120 out of 120 score on the grueling Putnam 2025 math benchmark. It even beats Google's Gemini in retrieval accuracy at the 1 million token limit. And most astonishingly, this entire massive model, along with all its infrastructure research, has been open source on Hugging Face for anyone to study. This model isn't just a technical marvel. It represents a fundamental shift in how we think about AI scaling. It absolutely proves that architectural ingenuity and strict mathematical constraints can match the output of massive capital and unlimited compute. Which leaves us with one incredibly important, provocative question to think about. If elegant math can outcompete brute force hardware today, what does the data center of tomorrow actually look like? Thanks for joining me on this explainer. I really hope you found this system design review as fascinating as I did.